I have the pleasure today to introduce Professor Martin Shepperd, to an elite distinguished lecturer at the Blickinger Institute of Technology. And Professor Martin Shepperd is the 2022 holder of the visiting professorship Tage Erlander that is awarded by the Swedish Science Foundation. And you might have read in the introduction, this professorship has been around for 40 years now, and Martin Shepperd is the first computer science professor that was awarded this professorship. And originally, Martin comes from Cornell University, and the Tage Erlander professorship 2022 is stationed at Gothenburg University. So please, the floor is yours.
Thank you very much. Thank you. I've been enjoying in the sort of build-up to this, playing around with the camera, which follows me around the room. So if you wonder why I'm kind of behaving erratically, that's the reason. So, okay, thank you for the opportunity to come and speak, and thank you for the warm welcome that you've already offered. So that's much appreciated. I'm going to talk about errors in machine learning experiments. That's the main theme, but actually it will take us in sort of some more general direction, thinking about how we conduct science, how we do science. So possibly you might think, I don't do machine learning experiments, so why am I here? But I would like to try and sort of cast the net a little bit wider. And in that regard, please feel free to, if you want to ask a question on the fly, please feel free to do so. And I think, Anna, some of you are not physically present, so I guess you can use the chat facility to raise questions. Obviously, if you're using chat, I think it's going to limit you to sort of fairly simple questions on the fly, and otherwise, perhaps wait until the end and I'll try and answer. I will be staying for the rest of today if you want to. I'm not sure class is organized, but hopefully there'll be opportunity to interact if you prefer to do it on that basis. So, okay, so without further ado, this is some work that I did with a whole bunch of people, and why is that? Oh. And credit where credit is due. These are some of the people that have contributed to this research. So 2 colleagues from China, Yuchen Guo and Ning Li, both from Xi'an. Then a whole list of colleagues from Brunel. I won't read out all their names, but these are some of my colleagues back in London. And they all contributed to this work. So they should get some of the glory, if there is glory to be had. And definitely, if there's any negativity or criticism, please focus it on my colleagues. It was nothing to do. As you've told, I'm really honored and privileged and slightly surprised that to be the recipient of this year's Tage Erlander Research Professorship. And that's been a fantastic opportunity. That started in January, somewhat interrupted by COVID and a few personal issues, but I finally moved to Gothenburg in mid-February, and I will be there until the end of September. So it's funded by the Academy of Science. So as I said, I'll be at Gothenburg University. While I'm on the theme of thanks, 2 of my colleagues from there, Robert Felt and Richard Talker, they worked extremely hard to make this possible, and I'm indebted to them as well. Just a little bit about Brunel. This is the sort of, it looks like a 1960s university, because that's what it is. So you see there's lots and lots of buildings. I think this photo was taken about 5 years ago, 5, 6 years, because there are a lot more buildings now. Like most universities, they just build and build and build. fortunately, there's still some green spaces left, so we haven't hit any boundaries yet. That's actually the department, our department building where we live. I think the photographer done a rather good job of it because it's not as beautiful as it might appear. But the main feature here is there is a duck pond. And occasionally it has fish in it. And then these birds, I don't know, probably know what herons are, but they're sort of large birds, waterfowl, and they eat fish. So they turn up and deplete all the fish and then fly away. More fish are sort of just restocked and then herons come back. So that's if you're like me, you might have quite a short attention span. So this is the sort of gist of what I'm going to say in about 1 minute. Okay. And then I'll say it all over again, rather longer and in a bit more detail. So in terms of in machine learning, computational experiments are the dominant paradigm. On the whole, analytic methods have very distinct limitations. So most of our understanding of behavior algorithms, the interaction between algorithms and data are through observation and through the conduct of experiments. And it's a busy area, a lot of work going on. So we don't just do one experiment, but there are many, many experiments. And then we try and build a body of knowledge through some sort of sense-making process of the results of lots of experiments. And for that to be meaningful, so that our sense-making isn't kind of contaminated or misled, then it's important our experiments are reliable. So, if the results are entirely random, then no amount of sense-making is going to save you because you're just trying to find sense from randomness, and that's not going to go very well. We, and for reasons I'll explain in a minute, finished up doing an audit of some experiments, published experiments, and we found of the order of 40% I'd had inconsistent results or basic statistical errors. So not getting kind of fancy or highfalutin as whether somebody should use the Schneider-Gruber transform before the aardvark procedure, which might be sort of moot, matter of opinion. We're saying fundamental statistical errors that everyone would agree is an error. Okay, so this isn't being kind of super picky and saying, oh, I wouldn't have quite done it that way. It's saying these are fundamental problems, okay, that would invalidate whatever paradigm or whatever approach that the authors were undertaking. So that isn't a kind of super cool situation that might concern us. To say, not far short of half of experimental results on the basis of this audit might be questionable. We'll unpack that in a lot more detail, but that's the sort of short-term message. Now, if we stop there, that's all very depressing. I think we have to acknowledge that we all, and that includes me, one of the things that's actually freaking me a bit is, I'll give you the details and so on this, but we've published our raw data and the analysis code and bits and bobs like that. And so I need to make myself open to scrutiny. So I hope there would be a sort of deep irony if an analysis of errors in other people's experiments contained errors itself. But I mean, we have to be realistic. It is a possibility. I think we have to be, have some humility and say it's not just other people, but we all potentially can make mistakes. So some possible remedies. I'm a strong advocate of open science. If we expose ourselves to scrutiny, it's more likely that if there are mistakes, then they will be kind of teased out. Another area that I would strongly promote is avoiding dichotomous inferencing. So this is the kind of mindset that says something is true or not true. So the classic is in null hypothesis significance testing, when you have some threshold, you set alpha to whatever value seems appropriate. You compare your p-value with alpha and say, oh, thank goodness, p is smaller than alpha, so it's true. There is an effect. Oh, rats, that's really annoying. P is greater than alpha, so it means it's not true. There is no effect. So you turn the richness of all your observation, your results, into this binary value attribute. So you're throwing away a huge amount of information. And it's going to be very sensitive, it's very fragile. So if you can imagine you had errors, it could completely tip your result from one thing to another. If we think in terms of our results more in terms of estimation of population parameters of interest, we might have slightly more graceful degradation. I mean, it doesn't protect you from all errors, but it might be a little less fragile. And I would sort of stress this again. It's kind of almost fun, you know, it's easy. We like to see errors and mistakes in other people's work. This is a sort of bit of a mock-up, a make-take from, I believe they're available in Sweden. It did seem from yesterday's talk, at least some people familiar. It's a series of children's books called Mr. Men. And there would be like Mr. Strong and whatever. They're slightly, well, the early ones were a little bit sexist. So it would be Mr. Strong and Miss Giggly and bad stuff like that. But anyway, so this is a sort of variant, which is Mr. Schadenfreude. They're sort of taking pleasure in other people's misfortunes. So we want to avoid that. I'm not trying to sort of, isn't it great these people make terrible mistakes, let's mock them. And same idea, different source of inspiration from The Simpsons, for those of you who have interest. This is one of the characters, Nelson Muntz, and his sort of trademark thing is he goes, ha ha, when anything bad happens, typically to Bart Simpson. But anyway, so I want to position this quite carefully, that I'm trying not to sort of, yeah, ha ha. I'm trying not to sort of name, you know, have a list of the 10 worst culprits or any of those kind of things, because I don't believe that is professional and it's not appropriate. Why? So after a fairly lengthy introduction, I'll set out the structure for the rest of the talk. So I'll give a little bit of context and try and look wider than just machine learning. I'll talk a bit about how we chose the studies that went into audit. And the spoiler is it was highly non-random. Okay. So some kind of analysis, some summary of findings, and then discussion of where does that take us and, you know, what should we do with this information? Okay. So over the last few years, there's been growing concern about experimental reliability, and more generally, not just in machine learning or computer science, or software engineering, but more widely. For example, there was some psychologists, they checked 71 studies that they published studies in referee journals, and they found simple arithmetic errors and a range of sort of very basic mistakes. So, you know, ballpark half of the studies they looked at were problematic. A much larger study, which was done by scraping PDFs from the web, you know, by some Dutch researchers, and they were looking more at the use of statistics and some of the problems with basic inferential statistics. Again, frequentist, essentially null hypothesis significance testing. So stuff like t-tests and so on. And they scraped approximately 250,000 p-values from these papers. And they found, again, astonishing, these are in refereed, decent journals, about 50% were problematic. That's not sounding like a great hit rate to me. Anyway, but I'm mentioning this because, it's not, I think, something unique to machine learning. Worse, or maybe better, I don't know, that in sense of the, if you think about, do we accept or reject a hypothesis, in 12% of those papers, the conclusion, so whether we fail to reject the null or we do reject the null hypothesis, was actually impacted by the error. So if they'd analysed it properly, they would have actually got the exact opposite conclusion. So you see, some errors may not be of huge consequence, but others may be. Right. In bringing it a little bit closer to home in terms of software engineering and machine learning, people started to raise issues about training data sets. So I don't know how many of you are familiar, but the sort of essence, well, a lot of the learners that are used to solve, say, software engineering problems, you have a labeled data set and use that to train your learner in order for it to then make predictions about unseen cases. So obviously, if your training data is in some sense problematic, that could distort the behavior of the learned prediction system. And label errors are a simple class of problems. So, for example, there was a more general study by Northcutt and some co-workers, and they found that some of the most commonly used data sets, there are repositories of classic, if you like, training data sets at UCI, which are used again and again and again, and they found problems in 10 of the most commonly used benchmarks. So that's slightly worrying. And similar problems with labeling being found more specifically in software engineering. Finally, if people want, I don't know if there's a simple way of distributing this, if anyone's interested in the slide. The references are the final slide of the talk, and there's a few of them, so they're a bit kind of micro, so you might actually want the slides if anybody, so maybe we can distribute them by some. Another sort of concern was by myself and I've forgotten, this is awful, I can forget colleague's first name. I'm ashamed, it's age. Anyway, we did this sort of review of people using inappropriate response measures. So in an experiment, you essentially assign your experimental objects to different treatments, and then you compare the different treatments in terms of what's often called the response variable, or the outcome, if you prefer. And so for machine learning, typically the response measure will be, if you're interested in classification, for example, will be how good your classifications are. And unfortunately, a large number of people use an inappropriate response variable. There's a different talk as to why it is, but you can trust me or not. Anyway, and we reanalyzed, we found about 12,500 results, and we reanalyzed them using an appropriate response variable and found that just over a fifth of those results, the conclusion changed direction. So if we're comparing learning algorithm A with learning algorithm B, which is a very typical thing to do for data set 1, then using an inappropriate response variable, learning algorithm A is better than B, and use actually a proper response variable, then you'd say, no, B is in fact better than A. So again, these things are not making us feel super cool.
I have a question on training sets.
Yeah.
What if I mean, there is nothing really wrong with the data set that you train it with, but if we all use the same training data set, isn't there a risk that we get some bias instead?
Well, there's some generalization issues that in as much as your training data set represents data or fails to represent data that you would actually encounter if you to deploy your learner, then it's a big problem. Another one is that people tend not to think about time. So you actually get not problems of non-stationarity. So things evolve over time. Yet, when you're doing your experiments, you just say, here's all the data. I have some random scheme to allocate the cases to different folds, and then I do a cross-validation procedure. And you're giving the learner a bit of a help because it's able at least to see a few cases in the future, as it were.
I'm asking because, I mean, there's been a lot of discussions about some sort of lab packages when it comes to experimentation, inspections and so forth over the years. And I'm always afraid that if we use, even if it's sort of representative in some way, I mean, it's still special. I mean, it's still one lab package that we use. And if applying method to that, well, how do I know how valid it is for other requirements documents, or in this case, for different?
Well, I think we're often driven by convenience. So, for instance, there's a lot of mining software repository type where it's in some sense convenient to mine data from open source software.
Well, I don't like the word convenient, but that's a different.
It's less effort. What would you?
I know the meaning of it. I don't like the consequence of being. It's convenient. You take what's available, but not necessarily the best.
Agreed. And the reason you make that trade-off is because it will take many hundreds of person hours and possibly high level of risk if I go and try and get some new sources of data, as opposed to very few person hours and very low risk if I go to, let's say, go and mine GitHub or something like that. and also, if the outcome in both cases is one paper, and that's the currency that researchers are largely paid in, is publications, why go to all the trouble of...
The value would be much higher.
In terms of contributing to knowledge and the benefit of society, undoubtedly, but scientists are mortal.
I know the reason, but I don't like them.
No, I think there's a very important discussion about the reward structure, the reward system for scientists. And that, I think, drives a lot of the behavior, including some things we'll talk about today. So I think these things matter. But I'm going to, for a few minutes anyway, going to zoom in a bit and focus on specific issues of how we conduct experiments. And then we can open up. Yeah. Another source of problem, which may also be related, is, sorry, some of this is a bit me-centric, and I don't know, well, just it. We did a big meta-analysis of 600 studies. And unfortunately, we found that who did the research was a much better predictor of the results than what they did. So let's say an experiment might be to compare, I don't know, random forest with naive Bayes or something like that. It's two type classes of learning algorithm. But knowing that someone had used naive Bayes didn't tell you much about the outcome. Knowing who'd done that research told me a lot about that outcome. And that's not a terribly good situation either. Now, the various competing explanations, and maybe some or all of them are true. So one possibility is some groups have more expertise. They've done a whole bunch of work working with random forests, and they do it well. So it could be expertise as an issue. Another is that my whole career, and I'm hoping to do some TED Talks, and yeah, everything is all about random forests. So I really am motivated to do random forests very well. Other stuff I don't care about, except it's the sort of benchmark I wish to be. So then you get all the distortions, like I'll take all the default settings for the hyperparameters and things like that. I'll, make no effort for that. But the random forest, I will chain 5 grad students in a basement for 6 months and I'm not going to let them out until they have managed to get implementations of my pet algorithm beats and benchmarks. And that's sort of below the radar a bit, yeah. So that might be another possible factors going on. I think it's probably cruel to chain grad students in basements. Just saying. And clearly these things matter. It impacts sort of decision procedure. One of the things about software engineering, we're trying to say this is applied research. We want to help the practice of developing software. So, if the advisors do X and don't do Y, then the consequences if that advice is not well founded. At a more micro level, it may well go some way to explain problems with reproducibility and replicability. So reproducible, I mean very basic stuff, like if somebody ran the same data, same algorithms should be able to produce the same results. You feel that's a sort of very low bar, minimum for science. But the trouble is, there are all kinds of good reasons why, good in quotes, why that might not happen. Some years ago, we had a research grant. We were looking at using case-based reasoners to predict software effort. Anyway, it seemed to be vaguely impactful research. And then that was back in the 90s. Then more recently, for various reasons, including I didn't really do much analysis of distribution results, which just published centers, which maybe wasn't a very good thing. Well, maybe we should be able to rerun this, reproduce my own research and then get some extra information from it. We couldn't do it. For a start, all the code had been written to run under Windows 95. So that was all bets up. I know you could say right now, well, we should Dockerize everything and that may solve some of the problems. But reproducibility isn't always that straightforward. Replicability is more, I think, concerned because we would expect that if we use different data, new data, how do our new results compare with, if you like, the original results? I think some ways that people decide whether replication quotes is successful are a bit kind of suspect, but you can see the principle that it would be nice to see if results are fairly stable. It might vary a bit, but not wildly. Or are they highly contradictory, which suggests that some other things, either our experimental procedures are pretty flaky or something else is going on. Why is that not doing that? Another difficulty, of course, is I was talking about sense making at the beginning, and a fairly formal or rigorous way of trying to do sense making is formal meta-analysis. And obviously, however rigorous and clever and arcane our meta-analysis is, it can't protect us if half the results are nonsense. So meta-analysis is not a way of turning kind of poor results into something meaningful. So obviously, problems with poor experiments or difficulty errors like this are going to cause us problems across the piece. So how did we kind of get into this? We were actually doing a systematic review and meta-analysis. We wanted to ask a related question, which was, in the field of software defect prediction, how do using supervised learners, that's where you train them in the sort of way I described with label data, compare with unsupervised algorithms, where you don't have the same requirement for training, labeled training data. And you can see that if we could get away without labeled training data, that could make, it could be very useful in a practice situation. It might be easier or quicker to deploy some of these learning algorithms. So that was what we tried to do. And we did a systematic review. But in order to do meta-analysis, we really wanted to have common response variables. And people had chosen different ones for all sorts of reasons. And we wanted to convert them all into one. In fact, there's a Matthews correlation coefficient, but that's not particularly relevant. And to do that, we needed to construct or reconstruct from the studies the confusion matrix. So we're kind of reverse engineering information from these papers. So we located 49 papers that were relevant, and these contained just under 2,500 individual results. And the people started to find that this doesn't make sense. You can't, like the positive cases and the negative cases don't sum to one, or the density defects is a negative number, or it was just kind of things that looked kind of weird, to put it mildly. So that kind of got us thinking, should we look at this more systematically? So as I said, I'm afraid we discovered inconsistencies. So just as a flavor, we looked in total, I think, at about, I'm trying to remember, it was 16 or 18, I think, rules we had, but these are some of the simpler ones. And you think, how could you possibly violate this? We would say the performance metric, so if you like the response variable, is out of range. So, for example, if it's a correlation coefficient, it's got to be bounded between -1 and +1. So if either the computed value or in fact the value that they provide falls outside, you know something is wrong. You might not know exactly what, you don't know necessarily how to fix it, but something is wrong. When, again, from the confusion matrix, we could recompute the defect density. So we require it's got to be at least 0. And we don't especially like defect density of 0 because it means you have no positive cases, which seems not ideal. Then, the other things are how does our recomputed defect density compare with their published one? Now you have rounding errors. We allow a margin of error, but they've got to be comparable. Otherwise, something is wrong. We don't know what it is, but we know there's at least one error in the paper, and so on. We didn't actually, but I just want to sort of say credit to these people because they thought about this, in fact, before we did, but they, in the end, we didn't use their tool for a range of reasons, but some of the ideas of looking at the consistency of the confusion matrix were explored by David Bowes and Tracy and David Gray back in 2014, in fact. So we're not the only people to think about this. Okay. So we did look more closely and we checked all 49 papers. And we also, as I mentioned, we looked at some simple statistical errors. So we focused actually on people who are doing inferential testing using the null hypothesis significance testing framework. So that's essentially from your test you generate. As a separate matter, I have deep concerns about the whole procedure, but for the sake of what we're doing here, we'll take it at face value, okay? So from your test, you generate a p-value, and then you compare your p-value with a threshold, which is alpha. Okay. So an example of a very, very simple error is failing to adjust for multiple tests. So clearly, if you follow this framework, you can say there's two errors that I kind of need to steer a path between. On the one hand, I don't want to reject the null hypothesis when I shouldn't. So if you do that, what you're doing is saying, yes, there's an effect here when there isn't really one. Conversely, you don't want to miss an effect. Let's say there really is an effect and you don't spot it. But typically, if you set, and people pretty much always do, set alpha 0.05, so 1 in 20, you're saying, I'm going to be more cautious about accepting things than I am about missing them. That's the kind of logic and whatever reasons you might go along with that. But you can see, if you didn't do just one test, 1 in 20 chance of being, if you set alpha that, and it's actually random data of saying, believing your random data has an effect. But if you did 10 tests, you've got more chances. If you do 1,000 tests, it would be remarkable. If you didn't, even though all you have is random data, it would be remarkable if some were not significant. So this is well known, well understood, and there are different procedures for adjusting alpha to take that into account. So an extremely simple but rather conservative approach is we divide alpha by the number of tests that we do, and the more modern ways of dealing. So again, in our audit, we don't get super picky about what's the very best, in quotes, adjustment procedure. Simply say, did they adjust for multiple tests or not? We don't care how we do it. It's did they try and do it or not? Because if they haven't, everyone would agree, even if we're buying into the null hypothesis significance testing, and you're probably gathering I'm not, but even if we buy into it, that would be an error. Of course, one of our difficulties is we couldn't always, even with these fairly sort of simple things that we want to check for, didn't come up with an answer because the paper didn't necessarily provide much information. And in fact, 14 out of 49 papers didn't provide us enough information for us to be able to fully answer all our questions. And that's, nearly a third. That's not, again, brilliant. But in terms of number of results, if you want to think of it that way, it was 823 out of the 2,500, so slightly more. Right. So 16 of the remaining papers reported inconsistent. We could say for sure something is wrong. We don't necessarily know what it is, but we know, that can't be true alongside this thing. Something was wrong. Maybe even both things are wrong, but at least one thing is wrong. So we could say there are difficulties with 16 other papers. And so these are so 16 and 19 plus the, can't remember how many it was now. I think it was 13 or something, 14. Yeah. So we've got 16 with inconsistent confusion matrices, 19 that were consistent, 14 didn't tell us enough to be sure. Oh, there you go. Thanks. You'd think by now I'd know my own talk. Sorry. Then similarly, we looked for statistical errors. Now, of all the studies, 13 use the null hypothesis, the NHST framework. So if you're not using the framework, it's not a relevant question. Say, did you adjust alpha? And of those, 7 out of 13, so just over half, didn't adjust. So that's a sort of clear-cut, very definite error. Okay. So the people doing statistical testing, unfortunately, it's not being done terribly well. Those are just some of the simple things we looked at. I mean, we were going for things that are relatively easy to discover. So they were, to use Klaus's not favorite word, they were convenient. So I fear that, the real situation may be worse. It's, like the famous, you go into a restaurant and you see a cockroach, you don't say, oh, there's the cockroach. You would say, it is infested. So unfortunately, one might feel that this is not as bad as it actually gets. Right, let's just, so to sort of try and summarize it, you need one paper actually made both statistical errors and had errors in the confusion matrix if you want to try and add everything up. So if you add the rows, we see we've got 16 confusion matrix errors, 19 with no error, and 14 that we can't test. But one of these matrix errors also had a statistical error. Okay, so that's the summary out of 49 papers. So then we wanted to unpack a little bit more and trying to do the sorts of papers make problems. Maybe they kind of cluster, maybe it's particular publishers thing. And I don't know if you've come across, it's popularized originally by a guy who was a university librarian at the University of Colorado called Jeff Beal. And he published and maintained for some years this list of what he called predatory publishers. So these are the sort of publishers that kind of send you lots of spam email. And basically the deal is this: they'll pretend to be a really top journal, and they have a very prestigious name like the Pan-Galactican Journal of All Knowledge. And if you send them, say, €500, they will fast track and this will be no meaningful reviewing, and then they'll publish your paper. You might be happy because the dean has been hassling you. Why aren't you, Martin, pull your finger out, why aren't you publish it? What am I going to do? What am I going to do? And then I get this email, save me. I'll send my dodgy work to the Pan-Galactican Journal of All Knowledge. I'll send them the money. I don't get hassled. Everyone, you know, the predatory publisher pockets €500 and everyone is happy. And it's easy money from their point of view. I mean, they may or may not, for a short while or for longer, put the PDF, you send them and host it somewhere. It's not, you know, there are tougher ways to make €500 than do that. So I don't know, maybe you should branch a business model. Anyway, so the list. And on the other hand, people have some concerns about this list. Not every journal that was on it possibly deserved to be on it, and it hasn't necessarily been very well maintained over time. And you get problems like people hijack a journal. So if a journal is closed or sort of becomes more, then people can set up a fake website, or they choose a name that's extremely close to the real journal. There are other things going on as well, but it's the starting point. Anyway, so I've sort of said a little bit about that. What we did notice is quite a high proportion of our papers are actually on this list. So we thought, maybe that's the answer. That would really take the heat off us as a community. It's bad researchers sending bad papers to bad journals, and all we have to do is stop all that badness and problem solved. Unfortunately, we looked at the odds ratio of there being an error between a non-predatory, so we call those good journal, compared with a bad journal, and in fact, see that it's fractionally over 1. I mean, look at the confidence interval, it's wide and it straddles 1. So 1 means no difference. So we essentially and sadly say there's really no difference between the error rate of journals that the papers go to bad journals and that go to good journals. That wasn't necessarily what we hoped, but that's what we found. However, it's quite big however, the predatory or the bad journals are more prone to incomplete reporting. So in more cases, we couldn't check for errors. And that does seem to be a phenomenon that it could be the less good or less sort of refereed outlets don't have the same standards, they don't require so much information about methods and so on. We also thought, well, what about the difference between conference journals? Because you might hope, I mean, generally, I'd say when I send a paper to a journal, I get more constructive reviewing, there's more chance to fix things, you have more iterations. I'm not constrained for the number of pages and so forth. So that might maybe lead to better quality. So we did the same analysis of conferences versus journals. And again, that's not exact. I mean, 0.6 is suggesting that actually conferences may have fewer errors. But again, look at the confidence interval, it's quite wide and it certainly straddles 1. So it doesn't look like on the face of it, there's much difference between conferences and journals. That's a shame. However, again, because of page limits, sometimes very strict page limits, time limits, and other things, we can see the phenomenon. The journal papers tend to have fuller reporting, so it's actually easier to spot the errors. So it may be that there are as many or even more errors in conference papers, but we're just not so it's not so easy to detect them. Right. Okay. So that's I say we looked at 49 papers. They were in the problem domain of software defect prediction. So we didn't look at all things. We looked at them because it was convenient. And we had some particular analytic tools to help us in doing that. I thought the error rate was surprising. It's not what I expected to find. Some of the audience yesterday, so I gave a similar talk at Lund. So I'm doing a sort of South Sweden, it's not really a road trip, it's a rail trip. And they took me to task. So why, surely I should have expected it, especially looking at other communities. And I didn't have a hugely good answer. I suppose maybe I thought, we computer scientists, we're just innately better people than other researchers. And we're more thorough and good at arithmetic and stuff. So we won't be. So this is just repeating what I've said anyway. But I mean, overall, in some sense, particularly if you consider that incomplete reporting to be some form of a problem, we're possibly looking at as much as 36 out of 49 papers had some kind of issue. If you think underreporting is sort of neutral, then it would drop to 22 out of 49. Still not a great hit rate, I'm going to say. I should also mention, not only thinking about journals versus conference papers or bad journals or bad publishers and good publishers, but even places that, you think are fairly prestigious, like IST, IEEE Intelligent Systems, KBS, some of those sorts of, solid, respectable journals were not immune. So these are papers that probably, gone through several review cycles, maybe typically had 3 reviewers for at least the first cycle and so on. And the stuff is still sneaking through. Okay, that was an audit. It wasn't a huge one. Let's think about some limitations. On the bad and negative side, there were almost certainly undetected errors because we focused on ones that are easy to spot. So in that sense, probably the situation is worse. However, on the other hand, some of the errors may be trivial, so they might make no meaningful difference to the conclusions. Let's suppose it's a huge effect that random forest is massively better at classifying data than naive Bayes. And the arithmetic errors or whatever is just noise. It's still a huge effect. That's possible, and it's not a thing we carefully looked at. We looked at a single, it's not even really a problem domain, it's sort of a sub-problem domain. We're just within machine learning for software engineering. We looked just at predicting software defects. So perhaps other communities have different behaviors. We only looked at 49 papers. There's hundreds of thousands of papers out there, and even within machine learning, there are still hundreds of thousands of papers. So as I mentioned previously, this still does fit with some of the other evidence. Problems of label errors, problems of people not being careful using right response variables, problems with different groups having pet algorithms or differing levels of expertise. So that's all a little depressing. What can we do? I think first things we should acknowledge, and I need to, acknowledge that it's easy to make errors. I mean, it would be flying in the face. You could say, well, half of everyone else is, not really up to date research. Thank goodness I'm the top researcher and I'm not in the bad half. But that's a bit of a stretch, I think. So I'm not going to say that. I think machine learning experiments are actually typically quite complex. It's some of the reasons why the treatments may be quite complex, in fact, may be multiple treatments, and we may also have quite complex data cleaning and processing prior to even using the data sets. So, for example, you might have feature selection where you actually have within your experiment, you will in fact be dynamically choosing what features to use from your data set, and feature selection algorithms are quite complex. You may be doing some kind of imbalanced learning. So typically for defects, fortunately, they tend to be relatively rare. So the positive case, which we're interested in, is the defect-prone software unit, and there are not many of them. And that's a problem that you have many, many times more negative cases than positive cases. And that if you don't do something about it, that can present your learner with difficulties. So there's a whole raft of analysis and treatment that we would use to handle that. Then typically we do something like a repeated measures experimental design. So every treatment or every algorithm is applied to every single data set. So again, there's some complexity there. Then our cross-validation, how do we actually, you will have repeated complex cross-validation strategies where you might run a 10 by 10 fold cross-validation, for example. So that's an awful lot of results, complex scripts, all sorts of things going on there. So you can see, errors might not be that surprising. So one, use tools. If you're going to try and hack it all with Excel and copy and paste from there and there, you are probably setting yourself up to make more errors. There are powerful tools out there, but perhaps, we need to develop more special purpose ones to support people in doing things like managing large numbers of confusion matrix and so on. But it should be lots of warning signs. If, let's say, a group do a whole bunch of complicated experiments and they don't use some kind of version control, Git or whatever, it seems foolish as you expose yourself to the possibility of wrongly using one version of something else, and then you realize there was a problem in your data and you updated these things and not that. And in the end, it all comes out and exposes itself as issued in maybe an inconsistent confusion matrix. So some it's computed on some data and other bits computed on other data. This is a little bugbear of mine, but I think we would do well to try and see, to try and move beyond results being dichotomous, like it's true, we supported it, it is a thing or it's not a thing. This idea that an effect size is exactly 0 or it's non-zero. Minimally, you're throwing away a lot of data, and I think you, as I say, you don't get very graceful degradation that, small errors or things like that suddenly become catastrophic, if you like, and your complete conclusion now goes in a completely opposite direction. I think we have to all say, look, despite the foregoing, we all make mistakes, and we have to expose our research and our tools, our code, our raw data, our intermediate results, and all the rest of it to scrutiny. And that means following open science principles. We are now rather belatedly trying to understand a bit more what's gone on, and so approaching some of the authors of studies, and we're trying to do it with courtesy and professionalism, and absolutely not have a hall of shame or this week's top 10 worst errors or things like that, which it's sort of this I don't know, rubbernecking. So when you drive on the motorway and there's unfortunately there's an accident on the other side, everyone's sort of like that, and then promptly cause an accident on your side as well. But we want to move beyond that, and we need to see people as human beings. I will not feel cool. As I said, I'm just anxiety that someone will say, Martin, you completely stuffed up and your results are, do you know what I mean? I'd really much rather that didn't happen. But on the other hand, if I'm going to treat science seriously, then I have to expose myself to that possibility and be grateful if somebody takes the time to look carefully and correct me, and then we think about how we update the record. So, which is the final thing, which is, better correction mechanisms, updating mechanisms. As a separate bit of work, we've been looking at retracted papers where something has gone badly wrong. It might be scientific misconduct, or it might just be poor practice, but something bad has gone wrong and the paper is formally retracted. But even that, the sort of mechanism, how that ripples through to the community and everyone realizes and so on, is not well managed. And maybe we need to think of a way, how can we make papers dynamic so that somehow you can not fix the error, and somehow all the versions and everybody knows, and the implications then are kind of propagated, and any meta analyses or what systematic reviews are then updated as well. And maybe that's hoping for too much, but that kind of thing would be brilliant. As I say, I thought I better practice what I preach. And here are a whole bunch of references that are way too small for you to read. But I could distribute the PDF. Thank you. That's it.